All right. The next page starts with another balanced equation problem.
Mr. Waddell, please call the front office. Mr. Waddell, call 2161, please.
All right, and this is showing the synthesis of iron 3 oxide with water. So first of all, you need to know that iron 3, it means it's a oxidation number of +3, so we'll drop that down here. And oxygen has oxidation number of -2, and we'll drop that down there. So there is iron oxide, and we're synthesizing it with water. So what happens when we do that? Well, you need to flip back the previous page where it talks about rules for synthesis and decomp. So that would have been a metal oxide with water. So if we look down here, number 6, where it says metal, the oxides of metal react with water, a metal hydroxide is produced. So we are going to go to iron 3 oxide plus H2O, and we are going to make a iron oxide. And remember, this was a iron 3, so we're sort of going to have to assume at this place for this synthesis that this iron does not change its oxidation number. All right, so let's check. Are we balanced? We have 1, 2, 3, 4 here, and we have 3 over here. So for our oxygens, we have 2 and we have 3. So we definitely are going to have to do something, and we also are going to have to take care of our 2. If we, for the iron, if we just put a 2 there, what does that do? That gives us 6 O's and 6 H's. So over here we have 3 O's, and we put 3 here. So we'll put that 2 in front of the Fe. If we put a 3 here, that should fix our problem. So now we have 1, 2, 3 O's plus 3 O's. That's 6. So there's 6 there. Let's check our H's. We have 3 times 2, that's 6 there. And whoops, so H3 times 2, so 6 there, and we have, so we're all good. There's our balanced equation, a synthesis, where we take this metal oxide plus a water, and we get a metal hydroxide. So let's look at a couple, and it says, using the electronegativity values, and that's the chart with all the little numbers, the periodic table with the little numbers from before, state whether the single replacement equations in the section above will occur. And so what that means is, coming back here, let's look at the one we did. We did lead plus iron sulfate becomes lead sulfate and iron. So let's just use that as an example. And you guys can check a couple more. Pb plus FeSO4 becomes PbSO4 plus Fe. So we need to go back to that periodic table. So I'm going to flip back to a couple pages before and look at this periodic table where we have our our electronegativity values. Now the problem with that table obviously is it doesn't have the names on it, so you're going to have to get another periodic table, and you're going to find that lead is number 26. So starting across here, 19, 20, 21, 2, 3, 24, 25, 26. Not lead, that's iron. Iron, I mean. All right, and then lead is much heavier. It's down here from radon in period, let's see, 1, 2, 3, 4, 5, 6, period 6, group 6, group 8, 7, let's go here. We'll just count across. So radon 1, 2, 3, 4, 5, 6. It's this row. And radon, acetine, polonium, bismuth, lead. All right, so iron is 1.83, lead is 1.87. So back here, back to our previous page, way back. All right. 1.83 and 1.87. All right, so this guy is a fairly high electronegative ion, and all of your anions are high electronegativities. They're acting like sort of like fluorines and chlorines and stuff like that. This happens to be acting a little bit more like an oxygen. But in general, it's going to have a high number. So maybe like a 3 or something. It's going to want to this only wants to happen when this number difference gets bigger. So if this is a number like, let's just S3. Well, 1.83 is a bigger difference between 3 than 1.87. So no, this one would not happen. The sulfate would actually like to stay with the iron rather than switch to the lead. Now remember, if I'm asking you to do a balanced equation, I'm not asking you to make that assumption. The only time I'm asking you to check is if I specifically say, well, this happened. Right, you guys can check a few more single replacements and basically do it the same way. You're going to have to look at the electronegativities of the things that have changed. All right, assuming that all the double replacement reactions on the previous page took place in a solution. Remember, double replacements have to take place in solution for them to happen, like our acid and base interactions. But also things like, let's just look, here's a the magnesium chloride lithium carbonate reaction. So we had the magnesium chloride plus lithium carbonate and became magnesium carbonate and lithium chloride. And we balanced it previously. We need to do that. All right, so the rules for this are not actually in these notes, but they are in your Unit 5 notes. So if you go and pull up your Unit 5 notes, and I'm going to grab mine really quickly. Unit 5A, reaction notes. The justification list for double replacements is in the Unit 5 notes. And what we have to look at is, are these things soluble in, are they soluble in water? What are their solubility rules? And so anything with a group 1 is good. So lithium's a group 1. Yep, soluble. Check. Doesn't matter what it's bonded to because it's the first rules. If it's a group 1, it is soluble. So this guy is soluble and that guy's soluble because they're both group 1. The second rule, nitrates are soluble. Well, no nitrates in this problem. Next rule, chlorides, bromides, iodides are soluble except a few, and those are things like silver chloride and mercury chloride, lead chloride, a few of those. So this is a chloride, so this is a chloride. So this should be soluble, right? Because we just said all chlorides are soluble except for that few list. So right now, we should be good on this guy. And we already were good on this. So now we only have to check, is magnesium carbonate soluble? So if we look, so magnesium would be a group 2. If you look down your list, the group 2s aren't mentioned yet. So the sulfates would be soluble, most of them. The chlorates, the ClO3s are soluble. The perchlorates, the ClO4s are soluble. Acetates are soluble. Phosphates are insoluble unless they're with like lithium. So lithium phosphate would be soluble, but magnesium phosphate would not be. Carbonates are insoluble, except for those of NH4, so ammonium, or group 1. So this carbonate is not soluble. So what has to be true? Well, these two, the reactants have to be soluble. What's this going to do? This will precipitate out. So if we did this, as long as our reactants are soluble, so we mix in some magnesium chloride and some lithium carbonate into this solution, they separate. We end up with this solution having lithium chloride left in it, and in the bottom, some precipitate out, we'd have some magnesium carbonate while all this lithium chloride is floating around in solution. So hopefully that makes a little bit of sense. I think I'm going to stop and we'll go through down here to redox B, and then we'll stop this video and we'll continue in the next. So what are always the products of a standard combustion reaction? We did a combustion earlier. Remember, you always get carbon dioxide and you get water, usually in the form of vapor for both of them. What two types of compounds are involved in neutralization? If you see neutralization, you should think acid and base. And remember, normally that means something with an H and followed with something with an OH, but there are other bases according to Bronsted-Lowry definitions, and we'll cover that later as well. What are the two products of a neutralization reaction? We are going to get some sort of a salt, and remember, a salt is just a cation plus an anion. Doesn't have to be sodium chloride, it can be any cation, anion. And we get water. So if you look at these, we've got, let's see, a handful of neutralization reactions. And I can tell that because look, we got a KOH, there's a base, H2SO4, that's sulfuric acid, H3PO4, phosphoric acid, NaOH, sodium hydroxide. Well, let's see, we've got HNO3, so that is nitric acid, and MgOH2, so magnesium hydroxide, HCl, so when we're talking acid, remember that's going to be hydrochloric acid, and calcium hydroxide. So these are all, we could go ahead if we want to and write in our H2Os. But remember, it may sometimes be easier to write in your H2Os like that. They're both the same, and I'm going to go ahead and do that for all of them because I know that one of the products for each of these is going to be water. And it's easier for me to balance HOH because then I can compare it back here to the H's and the OH's. So now I just have to figure out what my salt is. Well, the H and the OH are going to bond, so that leaves me with potassium sulfate. And potassium would have drop the oxidation number for the sulfate down. So we get K2SO4. This one, so the H's and the OH's are going to bond, and now we're going to get our sodium and the phosphate. That's Na3PO4. I know that's hard to see. K2SO4, Na3PO4. Next one, magnesium nitrate. So that is going to be Mg bracket NO3 bracket 2 because magnesium has an oxidation of +2 and I'm dropping it. And the last one is calcium chloride. Calcium is also an oxidation of 2. So at this point, it's just a matter of balancing. Over here, I have 2Ks, so I know I'm going to need that. And let me just go ahead and I'm going to rewrite this like that. Makes it easier. So now I have 2 OHs. I have 2 H's, so I know I'm going to have to put a 2 in front of that. And now I'm balanced. Okay, PO4, 1 PO4 here, 1 PO4 here, 1 A here, oops, 3 there. So I know I'm going to stick a 3 in front of that. So that gives me 3 OHs, 3 H's. Guess I need to stick a 3 in front of that. 1 H, 2 OHs. Let's check the others. I need 2 NO3s here, so let's stick a 2 there. Now I have 2 OHs and 2 H's. So I just need to stick a 2 in front of that. Calcium, only 1, but chlorine 2, so I know I need to stick a 2 there. So 2 OHs, 2 H's, 2 there. All right, so the next video will be covering redox reactions. You don't have to go into a lot of detail, but you do need to know how to find oxidation numbers. So we will cover that in the next video.